Hello everyone again to my YouTube channel. Today I will try to explain to you ML algorithms for linear regression. So in one of the last sessions I discussed with you, I tried to implement a model with a linear regression on problem of life satisfaction based on one feature, its GDP per capita. So today in this tutorial, I will explain you theoretically linear regression and what is the component of linear regression and how it's work and what is the math behind these algorithms. Okay, well let's start. Uh, okay, so linear regression is one of the main algorithms in machine learning, which is used for supervised machine learning. So I explain to you. So in machine learning, we have three types. So the first type is supervised machine learning. The second one is unsupervised machine learning, and reinforcement machine learning. Okay, and linear regression is in uh, is to solve regression problems. That means the first type of machine learning. They cannot be one, cannot be more problem. So it can be used for we have one independent and independent feature. That means here I'll explain to you before in the sections. We try to build in this model based on one feature. Okay, to predict life satisfaction. We want to predict the index of life satisfaction based on GDP per capita. So it's try to find the best fit line, which will have to locus for error all the point. Okay, let me explain to you. So here in these graphs, what we see here, we have equation y equal to mx plus c. So this equation is for represent this line, and the goal is to find the best line. Okay. So here in these graphs, we have 7 points. We have y1, y2, y3, 4, 5, 6, 7. This the original points. Okay, as we see here in this graph. You have this original point y1, y2, y4, y2, y7, and we have y hat 1, y hat 2, y hat 3, 2, y hat 7 is the fitted point, and the fitted point is in this line. Okay, this is y hat. This is the predicted values. Okay, here. So the best fit line is represented by the formula of y equal to mx plus c. The best line is represented with this equation. And our goal here is to find the best parameters for M and C. We need to give the best parameter, the best values for this equation. Well, let's see the component of this equation. So the first one, y, is predicted point. That means the target, the future target. So in the sessions, the previous sessions, y is considered like life satisfaction index, is dependent point. Okay, and x is given point, is independent point. That means is the GDP per capita in this last case, and m is slope of this function, and intercept the point of y at which line meet x at 0. Okay, we have slope and intercept. So here in this case we have slope and intercept is the derivative. We need to calculate the tangent of this line. Tan is equal to sin divided by cos. Okay, well, we have also the procedure for finding the best fit line, and to find the best fit line, so let's take into 3 point here with this coordinate 1 1 2 2 3 3. Okay, this is easy one, and this equation is linear. Y equal to ax if we want to represent it perfectly. Okay, well, here we have this 3 point with this coordinate. Well, um, so let's find y by using mx plus c. We want to find y based on this equation. So the case one, okay, let's consider this case one. Let's consider m equal to m, okay, m equal to 1 and c equal to 1. So in this first case, we want to give simple values for both of parameters m and c. And we have x as these 3 points, 1, 2, and 3. That means we give 3 values for this x variable. Okay, so in this scenario, we have 3 point or 3 predicted values, 3 y hats. So the first one, if I give for x1 and m is constant, is equal to 1, and c also is constant. That means we have here 1 times 1 plus 1 equal to 2. And the second scenario here with this x with 2 value, and we have also the constant value in m and c, and we found 3. Okay, and here we have 2. Here also we have 4. Okay, if we replace each parameter here with its own value, we found 4. So we got y hat values as 2, 3, and 4. So the y hat here is 2. Okay, we have 2, and we have 3, and we have 4. Okay, after we replace each variable here with own value, we found these values of 2, 3, and 4. That's it's what's called y hat. So our original values of y are 1, 2, and 3. Okay, the original values here for y. So here this is the original values we have here. Okay, let's continue. So after we found all these values, what we want to have, we so here is the process to finding the best values. Okay, well, the next step here is to find the cost function using this formula. Okay, as I told before, so we have here this cost function with this formula. Okay, it's 1 divided by n, summation of e go 1 to n of y e minus y hat t squared. So this is the formula of cost function, where n is equal to a number of points. Okay, so here as we see all, see the cost functions. Okay, this is the formula of cost function. And as I said before, we have ye is the original y value. So in our case here, in this case 1. Okay, so this is my original values we have here, 1, 2, and 3. Okay, and y hat is the predicted values, fitted y values. Okay, so here what we want to is to replace all these values in this formula and see what we can got. So we have 1 divided by 3 because of course we have 3 points, and we have the summation of all these 3 points we have here, e minus y hat squared equal to 1 divided by 3 times 2 minus 1 squared, or 1 minus 2 squared. This is the same thing because all this value we can got here is will be squared. That means will be positive falsely. Well, we have 3 minus 2 squared plus 3 minus 1, 4 minus 3 squared. So this give us 1 divided by 3 times 1 plus 1 plus 1 plus 1 3 times equal to 3 divided by 3 equal to 1. So the cost function in this scenario is equal to 1. Okay, well, at m with m at at m equal to 1, we give for m the value of 1 and c equal to 1. We got this the cost function as 1. So at the error is 1. That means all the point we have here is for our total error of all these predicted value. So here it is so it's not here but in this point, okay, so we consider here. So the error of all these predicted point is equal to 1. The error based on this cost function is equal to 1. So our goal here is to optimize this error. That means we need to find the least error, the least error. Okay. Well, with these parameters m and c with 1 as a value, we found cost function equal to 1. So let's pass to case 2, second scenario. Here we take in m equal to 0 and c equal to 1. If we replace in this first equation all this value, we found 1. Here m x plus c, m as a 0 times 1, because 1 is the original values of y, plus 1 as constant. We found 1. And the second scenario, the syntax. 0 times 2 plus 1 equal to 1. And that 1 is equal to 1 also. Here, when we pass into cost function, we found 1 divided by 3, 0 plus 1 plus 4. Okay, after calculation of this, 1 minus 1 squared equal to 0, 2 minus 1 squared equal to 1, and 3 minus 1 equal to 2 squared equal to 4. And the final result is 5 divided by 3. Okay, this is the cost function. Here, after we change in the m and give it 0 as a value, we found in the cost function uh, 5 divided by 3. So let's pass to third case. Let's take m as 1 and c equal to 0. At this time, we found 0, we found 1, and 2 and 3. Okay, well, here in this cost function, 1 divided by 3, 1 minus 1 squared plus 2 minus 2 squared, 3 minus 3 squared, and the final result is 0. Okay, so on these three scenarios, we have the first value of the cost functions is equal to 1, and the second one is 5 divided by 3, and the third one is 0. So out of case 1 and case 2 and case 3, we got the global minima cost function at m equal to 1 and c equal to 0. Because as I told before, when we applied cost function, the global goal is to optimize the minimum. Okay, to optimize the errors. That means we need to choose the lowest cost function, lowest value of cost function. Okay, so here the global minima of cost function at this time with this parameters m as 1 and c equal to 0 is the 0. Okay, so we're predicting y equal to mx plus c. We are can taking m equal to 1 and c equal to 0. That means in the future predictions, when the new simples come in for our model, we need to work with it with this value. We need to give for our equation c equal to 0 and m equal to 1, and we replace the x with the new value we have to found m or to find y as a predicted value. So with these cost functions, we need something other help us to understand how all these things work. So as we see here in these graphs, we have this convex function. Okay, this is the convex function. This is like that. Okay, if sorry if my writing is not clear, f equal to, in this case, for example, x squared. Okay, x squared. Well, how are the function? How we have algorithms behind this cost function, of course. So each value, negative or positive, is still positive because minus one, for example, minus one squared is equal to one, minus two squared is equal to four, two equal to four, one squared equal to four. Okay, so for this reason we have these positive values here this time. Well, here what we want is to find the global minimum. So the global minimum in this case is here. Global minimum. All point on this side will be their derivative slope as positive. So the slope of this equation it will be positive. Okay, so our slope is going here in this, and here will be negative. Okay, fraction the derivative here it will be negative to find the optimal or the global minimum. Here this algorithm is called also gradient descent. It's one of the fundamental and important algorithms we have, the gradient descent. That's also work in neural network in deep learning. Okay, and these algorithms they will show it now here. Um, so we'll get in the cost functions. We'll use something called as convergence to global minimum. To get the global minimum point, we have current functions, current function cost functions minus alpha times slope. Alpha here. Okay, so this is the algorithm of convergence here. Okay, where current functions, that means cost functions as we see before, and we have alpha is learner rate. That means step I will use here to do this derivative. Slope is the derivative. Okay, that means if we have, for example, let's take an example here. I swear. So we have, for example, value of 2 in cost function, and we have learner rate. Let's take an example value of 0.0000, okay, times 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 the slope we have. Let's take an example of 1. That means here the convergence here is 2 minus 0.001 times the slope of function, and as algorithm is continue up finding the global minimum. Okay, this is the process behind this convergence algorithm. Okay, I hope that is clear for you. Here we have two scenarios. So if we have this slope positive, derivative is positive, convergence is will be like that. We have the current functions minus this slope positive value. That means which be less than the current function. Okay. Okay, this means the convergence will be less than the current function we have. If the derivative is negative, and this is negative, and so this is negative and this is negative, this will give us positive, which will be greater than the current function. Okay, if this derivative is negative and we have for this step we use here in this alpha as a value, small value, -1 times -1 give us positive, so which will be more or greater than the current function here is the inverse. Okay, if this is negative and this is positive, So all these things will be negative value. This means will be less than the current function. Okay, we'll take learning rate alpha. If it is very high, there may be times it can find better than global minimum. That means if we give for alpha a high values, doesn't mean we don't have any chance maybe to find the global minimum. Because here in this graph, if we take in alpha with some high value, is, is for example give it to randomly, that means the derivative we will go here and go here and go here and maybe go again return to this first position and go. That means this will be never got this global minimum. So for this reason, it is necessary to affect a small values for alpha to find the global minimum. Okay. Well, so but if we take in at least if we take in this mean alpha, although it's move slowly, okay, it's with slow step, but can find very global minimum. Okay, if we give for alpha a small value, that means we can help us to find the global minimum because we go with a small step. Also, here we discuss with one feature. That means we have a goal or target variable with one different variable and different variable here. So let's see multilinear regression. So it's the same thing. So in multilinear regression, we have the syntax, the same logic behind. But we have more than one independent feature. That means here is if we consider this representation, in first scenario we discuss with x and y. Y as a target and x is independent feature. But now we add in the new features called z, for example, and the representation graphs is called because we go to plan. If we have the feature that's in 3 dimensions, it's a plan. Well, here we have a plan. That means we have more than one feature. Instead of 2 dimensions line, we'll use three dimensions. That means plan. Box here to fit the point. Formulas for plan depend on the number of independent features. So here we have a formula. So if we have two features, this equation of linear regression is coming like that. Y equal to m1 x1 plus m2 x2 plus c. Here, if we remember all in decision of when I try to implement a model with a linear regression based on a feature of GTP per capita, I can add other features, for example, like age or maybe like gender, okay, as a feature. Then at this time, I need to find the best value for M1 and the best value for M2 and the best value for C. And X1, X2 is the given value. Okay. If I have three features at this time, this equation is come like that. So Y equal to M1, X1, M2, X2, M3, X2, and C. That means I will find the best combination of values for all these parameters we have here. If I have 5, also the same thing. I need to find the best parameter of M1 to M5 and plus C. Okay, C is called twice. Okay, well, and that's work for in features. Maybe we're gonna have more than I don't know. Your projects gonna find a lot of features. Can consider a lot of features. I will try to build in video models with diabetes people to show you how that is important. Well, the equation is coming like that. I need to find the best combination of values for all these parameters. That's what's called linear regression. regression. Okay, and of course we have the polynomial regression. Polynomial regression is used when data is not linear because of, and most of the time, of course, we don't have data like that. But this line kind of found the data like that. Okay, is represented like that in these graphs in this plot. Well, at this time we have one concept called degree of freedom. Degree of freedom of this polynomial. Okay, represented like that. The degree of freedom of all this. So higher the degree of freedom, higher the baseline will be. Okay, when the degree of freedom is high, that means we can found the best line and all these combinations. So if we see this degree of freedom of 1, that means we have a straight line. But we have degree of freedom of 3, the equation is coming like that. It's like equation cubic function. And if we have degree of freedom equal to, we have this representation first. Okay. Well, the degree of freedom is very important when we're facing a problem or polynomial problem. Okay. Well, this is the formula. It's easy. We have m0 x1 degree 0. We have so we have the polynomial degree and we have the formula. It's the same thing. The difference we have here is the degree of freedom, as we see here. When the degree of freedom is high, the baseline is gone. Okay. Well, we have type of cost functions, of course. So we have the mean squared error. The first type is mean squared error here. We have this is the formula. Here is the number of points. Maybe we're gonna face in a huge number of points. At this time, we need a much of time to calculate all the errors, and we have showed actual value and we have the predicted one. But what is disadvantage of this cost function? Is not reduced to outliers. The outliers simply is the values we can have in the extreme of range. Okay? When we try to see the distribution of some variables, for example, like that, sorry, okay, we have this bell curve of distribution. You see the outliers, kind of found the outliers here and here, and we have also the strategy to minimize these outliers because we have a lot of algorithms is impacted with outliers. Okay? And the method or this equation of cost function is not work with outliers. If we have a lot of wires, we have noise in our data. That is very hard really to find the best values. Okay, it's not reduced with outliers. Doesn't mean it's impacted with outliers. The outliers here and here this will be impacted, and the value will be very high. Okay, imagine if we have some outliers, it's big, and the difference with square, that's mean we're gonna facing high values. Well, and we have the second one. It's mean absolute error. Here, this is formula 1 divided by n, the sum all this point we have, and absolute value of the difference. Absolute value of the difference. That means the actual value minus the predicted one, with ups or the absolute value, and is reduced to outliers. We don't impact it with outliers because if we have difference between the predicted value and the actual one, the difference will be clear, but is not big like when we're using the cost function with square error. Okay, and the values, of course, we will be least because it's not squared, and it's obvious to outliers as I said before. When we implement the EDA, exploratory data analysis of our projects, and we discover the if we have less outliers, it's okay to work with mean square error, but if we have outliers at this time, it's necessary to use this mean absolute error. Okay, and we have also the third one here, the fourth one square error. So is a mean error square square. Okay, the root. So we calculate the mean square error and we add it in the end the root for this equation. So it's not reduced of course with outliers, and the values will be less. Okay, this is the advantage of this method. The value will be less, but is not reduced with outliers because it's the same equation, but we add in the root in the end. Well, to check in the accuracy of our models, of course, we have one in regression linear. Okay, in regression linear, we check in the accuracy of our model by R2 and adjusted R2. So R2, this is the formula, R2 equal to 1 minus ZDL and divided by this total. Here what we do, what is the math behind these things? We try to check at the first time we draw this line. If we have here Y and we have here X, what we do is to calculate the mean of Y, that means the predicted or the target one. We calculate the average and we store it here. Okay, this is the average. And we try to calculate the mean based on these lines and we do the difference. So the other formula of this r squared is mean. So my writing is bad. I'm so sorry if not clear. So mean of y, okay, minus what? Minus the mean of the other variable here in this. Okay, sorry. Let me be sure. No. So mean of y minus mean of this line. Okay, the piece line here. That's called the residual. Divided by y, divided by the total here. That's mean divided by this average. So this is the average of y minus the residual divided by total or divided by this equation or the mean of this line. At this time, why this r square is important because we give us by rate. If for example in some scenario we apply this parameters of a square and I found for example a 60%, r2 equal to 16%. What that mean? That mean the 16% of variation between x and y is explained. It's captured by model. Remember, in case of r squared equal to 16, that means 16% of variation between x and y is captured by model. That means this relationship is able to explain 16% of variation. And the other case, if r squared equal to 1%, for example, that means this relation between x and y is very hard to explain because just we have 1% of variation and 99% of variation will be maybe explained by other factors. We are not able to explain this variation. That is why a squared is important. And also we have r. Okay, we can find r in some documentation. We can find, for example, r equals some values. For example, r equal to 0.5, and we need to square it to understand. That means if r equal to 0.5, that means 0.5 times 0.5 equal to 0.25% of variation is able to explain by model. This is why r is important, and does depend on correlation of variables. The correlation does mean we need to understand the sense of this relationship, how it is positive, if positive or negative. I don't know. For this reason, we use these parameters as squared and correlation. correlation, all these things is important really to use it. We try to build it. And we have also resisted squared here. This is the formula. It's we calculated the a squared and we try to apply this formula to understand the relationship exists between two variables. So I wish to understand this deep concept of linear regression because it's the basic one before trying to jump in the more complex models, okay, like random forest, like XGBoost, like those deep learning also. I wish you happy learning for everyone and see you again in the next session. Bye bye.